after that, so I will summarize our research questions and findings, and after that I will also describe some further observations that we had following those results. So as I said, the main focus of the research is stationarity. It's clear, everyone knows that financial time series are not stationary objects. In these very simple slides here, you see the log returns on certain reports, and you see clearly there are some price trends and some volatility clusters and stuff like that. The problem is that so far in literature, this phenomenon has been modeled using like classical econometrics or augmented time series models like hidden Markov models or augmented Garch models and state-dependent models. I believe most of you or all of you have been dealing with such models, and as you know, they are problematic. They are problematic in many ways. First of all, they don't cope well with dimensionality. They suffer heavily the cost of dimensionality as the dimensionality of the problem. So as you include more stocks, for example, or more assets, the estimation of these models is very inefficient, is very computationally expensive, and therefore mostly they remain univariate or small dimensional in their essence. This is clearly a problem. This is clearly a problem because we know that financial time series are multivariate in their nature. The patterns and the dependency structure plays an important role both in defining and understanding the structure of financial markets and also for forecasting purposes. So our goal here was to try to understand these states, these clusters in temporal clusters in financial time series, but using the multidimensionality of the problem, being aware of the multidimensionality of the problem. So to do that, we introduced this novel model that we call EEC. So the intuition comes from previous literature, and particularly from a paper published in 2018 from Stanford that were studying electrical vehicles, in particular, like the time series of sensors in electric vehicles, driverless cars. The idea here for us is to cluster stocks not from a asset perspective, but from a time perspective. Okay, so each observation for us is a time observation, including all the stocks in our samples. You can see here, this picture here is a better example. You have a number of time series. So on the horizontal axis, you have time. On the vertical axis, you have the stocks. And what we do is to define clusters that include multiple observations. Okay, we want our requirements were we want these clusters to be interpretable. We want these clusters to be parsimonious so that we can run it efficiently in a multivariate environment, and we want them to be temporally consistent. This is something that usually, particularly in econometric literature, is not treated. What I mean is that it is easy to have clusters, temporal clusters that make sense, that are intuitive, but usually they are not practically feasible, because what you get is a model that switches continuously. Okay, so in our case, we're using daily observations. The obvious outcome would be to put one day in one cluster, the following day in another cluster, and so on and so forth. Practically, this is a big problem, because suppose you're a trading firm, you cannot switch your portfolio every day, because the trading cost will outcast the outcome of your investment strategy. So what we do want is to have our model to be temporal consistent. So to switch in a cluster, to cast an observation in a different cluster, only if there is a marginal gain from doing this switch. Okay, how can we do that? What we've done is to consider different measures distance. Okay, so for each cluster, for each observation, we compute on a observation-wise fashion a similarity or a distance metric. I'm talking here in general terms because we consider different similarity measures, particularly the Euclidean distance, the Mahalanobis distance, and the likelihood. And what we want to do then is to maximize or minimize, based on which one we are considering, this distance measure, but penalized for the switching. Okay, maybe this picture here makes it clear. What is this picture here? Here you got three series. These three series are the daily observations of the likelihood for different clusters. Okay, so what we do is to compute the likelihood corresponding to each observations, assuming that they were part of a different cluster each time. Here, the number of clusters is an hyperparameter, so we fix it, and there are many ways in which we can fix it. Everything else is automated. So what I'm saying here is that what we do is we cast observations in a cluster if the likelihood is higher, and if, looking at the previous observations, it is worth to switch it. That's the intuition. The way it works is simply maximizing or minimizing the distance metrics plus a penalization term. As I said, we tried the Euclidean distance, the Mahalanobis distance, and the likelihood distance. For the purpose of the clustering in our paper, we focused on the Mahalanobis distance. Okay, here's the question. If you look at this, this cannot be maximized with a closed form solution. Okay, so we have to do an iterative process. Our iterative process is very similar to an expectation maximization algorithm, particularly if you take out the penalization term and if you use the likelihood here. This is exactly an expectation maximization algorithm. The algorithm starts with assigning randomly observations to each cluster. I repeat, the number of clusters is an hyperparameter. Then we have two steps that are repeated iteratively until convergence. In the first step, we estimate the parameters of the clusters, that in our case are just the covariance metrics and the means. Based on these parameters, in the second step, we assign observations to each cluster based on which cluster maximizes the likelihood. Here, the picture here, okay? For example, this cluster here, the orange one, maximizes the likelihood at this time here, around 2007, while the next observations, the yellow cluster maximizes the likelihood of the observation, okay? So that's what we do. If you maximize without considering time and considering likelihood, you're doing an expectation maximization algorithm, so you're maximizing the likelihood. If you penalize it, you need to take into account all the previous observations. Okay. Computationally, this is a huge problem because what you're doing is exactly what is drafted here. Okay, so you need to assign each observation to each cluster, taking into account both the likelihood and all the previous assignments, because you are assigning if it is worth it, right? So if your gain in terms of likelihood overcast the switching penalty. So this is, as I said, a computationally very inefficient task, because you would be supposed to compute all the possible paths, okay? So all the possible combinations between of assignment that is highly computationally, gets very easily unfeasible. The complexity of this thing, of this assignment is of order k times t, where k is, t to the power of k, where t is the time and k is the number of classes. To solve this, we use the Viterbi algorithm that allow us to do this in linear time and makes it computationally extremely efficient. And that's our second step. So what we do, given the parameters of each cluster, we compute the likelihood of the distance matrix for observation-wise for each individual observation, and then we assign the observations to each cluster, maximizing or minimizing, taking into account the penalty switching term with the Viterbi path. Okay, these two steps are iterated until convergence. That's our algorithm. In our paper, we presented two experiments. Our first experiment is focused on clustering. So we look at the clusters that we obtain and we analyze them. A second experiment is focused on forecasting. Okay. For both the experiments, we use a data set of daily log returns from 1995 to 2015. We considered a base universe of all the stocks that ever entered the Russell 1000 index, and then we pick randomly 100 stocks among those continuously trained. We did a sampling analysis to show how robust our analysis is and to show that we are not like biased on picking stocks. What we obtained is what you see here. So here in this picture, you see the result. The time series charted is the average market return, so the average return on the 100 stocks that we picked. We clustered our sample using only 2 clusters here, and as you can see, first of all, a good thing, the result is pretty intuitive, right? So you have an orange cluster that obviously corresponds to kind of crisis times, and you have a blue cluster that corresponds to bull times, so periods where the stocks displayed positive returns. The very good thing from a practical perspective is that the clusters are very consistent. So throughout the whole sample, we only had 208 switches in regime. Okay, this means that you don't have an algorithm that switches continuously on a daily basis, but it's pretty consistent. When it picks a regime, it sticks to it. Particularly, we found that the average length of the segment is 28 days. So on average, when the algorithm picks a cluster, it stays on it for 28 days on average. And looking a little bit deeper on what kind of clusters we found, you can see here that our intuition is confirmed. So we found a cluster where most of the stocks, so more than 75%, have a significant positive Sharpe ratio with positive means and relatively low variances, standard deviations. And the second cluster with mostly negative means and higher variances, standard deviations. So our 2 clusters are intuitive, they make sense, and they correspond to something that we do observe in the market, and they are time consistent. Mostly, we've done this experiment with 100 stocks. We have resampled it. We have done it with many more stocks, so we tried it, and this is computationally very feasible. Second experiment, forecasting. So here there are many ways. Given that we have our algorithm and we like how it works, we like the kind of clusters that we find, we could easily use the same algorithm to forecast. Okay, so we would just need to forecast our distance measure, and then we can use our penalized maximization process. However, here, for the purpose of our paper, we preferred to keep it simple, and we just trained a logistic regression. What we've done here is to use as an independent variable a likelihood ratio, that is the ratio of the likelihood of the 2 clusters. Okay, and our dependent variable is the state, is the cluster. Okay, 1 or 2. We trained this logistic regression. We used our train set where we included as you can see from the picture here, everything up to the crisis, and then we wanted to keep the crisis out of sample to see how it performs. And again, it's a pretty simplistic model, but still we obtained a 55% accuracy in our forecasting experiment. That's pretty good. If you think about it, I mean, given that each cluster has very specific features, characteristic, knowing that you can most of the times pick correctly which cluster you're going to be in is potentially very powerful. And again, this is a simplistic example where we prefer to keep it simple to enhance intuition. So one more thing, I said that our clusters are defined simply only using a variance covariance matrix and a mean vector. For the variance covariance matrix, we use the TMFG logo filtered inverse covariance. Why? Here we show one of the reasons why filtering the variance matrix played a very important role. What you see here in this picture, in this chart, is the daily likelihood for just one cluster. Okay, the black lines are the daily likelihood observations using a full covariance matrix, and the red line, the same thing. So the daily likelihood observations using the filtered matrix, so the TMFG logo matrix. As you can see here, it's incredibly, significantly more robust and stable, the likelihood computed when filtering the matrix rather than the other. It's clear from the chart, it's a complete different order of magnitude. And most importantly, you can see here that the likelihood tend to be higher in train. So the green vertical bar divides the training set and the test set. The training set, we estimated the parameters, and then we computed the likelihood throughout the whole sample. As you can see, in train, the full covariance matrix likelihood tend to be higher. That's expected, since the full covariance matrix likelihood is the theoretical maximum attainable. But still, the filtered likelihood is much more stable. Out of sample, instead, other than being much more stable, it also performs much better. Okay, so that's the reason why we used the filtered matrix. That concludes our findings for the paper that we published last year. However, I mean, looking at these results, we had like a couple of more intuitions, couple of more questions to answer. Two of them particularly are, first of all, so the portfolio construction literature, particularly, you know, the Markowitz mean variance optimization, proposes an optimization framework, and then he says, okay, the problem is how we do estimate the parameters. But why is that? Our intuition is that it works well if our parameters are good in test set. So if we estimate some parameters in a train set, then we build a portfolio. If our parameters are good in describing the future, so the test set, our portfolio will perform well. But why? Because they're going to have, so the likelihood of our parameters representing the future is high. Is this true? That's the first question. Second question is, okay, we have looked at the likelihood observation-wise. So these are very interesting objects because, so this is a series, a univariate series constructed from a multivariate objects. That is our like stocks returns and the covariance matrix. Okay, that's a very interesting object. And when we look at clusters in our experiments, we highly refer to these kind of measures on a daily, so observation-wise. And the question is there any pattern? Is there any kind of behavior in this object that we could extract, that we could try to model? And at the moment, we were trying to answer these two questions. For the first question, so in terms of portfolio construction, what you see here is that is the likelihood that we obtain using a filtered matrix and a full covariance matrix in train and out of sample, as the number of observations used in train to estimate those parameters increases. As you can see, in sample, the more observations you use, the higher the likelihood obtained, so this is the mean likelihood throughout the whole train set, increases. And as expected, again, the likelihood in train using the full covariance matrix is higher. Out of sample, however, different story. The full covariance matrix performs not very well when few observations are used. As more observation and included, it starts to get better, but still a filtered matrix does much better out of sample. And so following our intuition on portfolio construction, the conclusion is that, okay, given that the likelihood of a filtered matrix is better, the performances of a portfolio built on a filtered matrix should be better, isn't it, right? However, what we found is that in terms of performances, this is not true. Okay, so a portfolio built on parameters that have a higher likelihood out of sample do not necessarily performs better in terms of returns, okay, but it does perform better in terms of variance. So what you see here is the variance of a portfolio that is built on the same mean parameters, but using two different covariance matrices, so a full covariance matrix and a filtered covariance matrix. As you can see, the analyzed out of sample standard deviation of the portfolio is much lower if the portfolio is built with a filtered matrix. And indeed, there is a relationship between the likelihood out of sample and the variance of the portfolio. As you can see here, the two charts on the right, you have the likelihood versus, sorry, the variance of the portfolio on the y-axis and the likelihood on the x-axis for a portfolio constructed with a full covariance matrix on top and a filtered matrix at the bottom. Okay, as you can see, in both cases there is a relationship with the variance diminishing as the likelihood increases. However, this relationship is much clearer with the filtered matrix, when the filtered matrix is used. One last thing, I'm trying to stay into the 20 minutes that we wanted to invest. One last thing, as I said, the role of the observation-wise likelihood. We'll be looking at this object, and here I very quickly just put two observations, two outcomes of our analysis. Here, what you see is the autocorrelation function of the univariate series of the likelihood. So this result is actually something that we are looking with quite a lot of curiosity, because as you can see, it seems that there is quite a significant and clear seasonal pattern in the autocorrelation of the likelihood. Okay, the chart on the left is done with 100 stocks taken randomly. The chart on the right is an average across 200 resamplings that we've done through stocks and through time. Okay, so in each resampling we picked a different time period and different stocks, and still the seasonal pattern is confirmed, and in most of cases is significant. Again, this is just a first observation, and these are working paper we're working on at the moment. Yeah, I put in here the main references of the results that I provided. I think that I'm staying into 20 minutes. So guys, please, if you have any question, more than keen to answer.
Thank you very much, Pier Francesco.